Hello, I'm Susan Nash, AAPG. I'm delighted to welcome you to this Department of Energy sponsored GEODE project sponsored webinar that's being administered by AAPG and organized by AAPG. Would like to thank Eugenia Torregosa, who will say a few words, but we have a team of experts in this 2-day webinar series, and really happy to introduce our first speaker, Eric Stautberg of Colorado School of Mines. And in the meantime, I'd like to just welcome Eugenia.
Hi, my name is Eugenia Torregrosa. I'm part of the GEODE project. I'm also a project in space. GEODE, for the ones who don't know about it, it's GEODE. It means geothermal energy from oil and gas demonstrated engineering. And basically, this event is one of the many others dissemination events organized within this program that was kindly organized by AAPG. And basically what we were after with this 2 days workshop is to provide practical and hands-on webinars or workshops in which people can take away practical knowledge of how to do things. And especially for the people that work in oil and gas that is transitioning into the geothermal world or want to learn a little bit more about the geothermal or how the subsurface evaluation is done in geothermal, and how to apply their current skills in oil and gas for geothermal. And that's all from my side. Thank you, Susan.
Oh, thank you. Well, that's great. So today we'll have Eric Stautberg, Kellen Gunderson, and John Holbrook. And I'd like to invite you, Eric, to share your screen, and we can start the presentation. And as a reminder, I'd like everybody to be sure to turn off your camera so that we can conserve bandwidth and not be distracting.
All right. Good morning, everyone. Can everyone see my screen? Uh-oh. Nope.
It looks great.
Okay. Well, I want to start by, of course, thanking everyone for joining today. It's pretty amazing to have... is my screen sharing paused?
It's all good.
It's all good? Okay. I have a weird notification over here. Okay. I want to thank everybody for attending today, of course. It's amazing to have this many people interested and excited about geothermal energy and showing up to these different webinars. My name is Eric Stautberg. I'm a PhD candidate at Colorado School of Mines in the Department of Geology and Geological Engineering. And I'm working on a kind of geothermal exploration project in South Texas for my PhD. For my background, just quickly, I have a bachelor's of science in geology from Texas A&M, a master's in science and geology from UT El Paso, and I worked in the oil and gas industry for 6.5 years at Anadarko and Oxy, working onshore U.S. exploration in various onshore basins before deciding to go back to school and do my PhD in geothermal energy. So with that, we can go ahead and get started. I like to start these presentations by just talking about, what does the geothermal picture look like in the U.S. currently? And so the next couple of maps and figures I'll show are from the EIA's website, the Energy Information Administration. They have a ton of great data out there on everything energy. So, if you're interested, go check that out. The map over here on the left shows the states that currently produce.
Eric, I think your presentation is frozen.
Yes. Yeah.
It's always something, right?
Yeah, you might unshare and reshare.
Yeah.
Okay, it's working now. There we go.
There it is. You can see the map.
Yes, great.
Oh, perfect. And it's always the first presentation that has the glitches, right? Anyways, so the map over here on the left is from the Energy Information Administration from their website, February 2024, and just showing the states that currently produce geothermal power in the U.S. Is my screen sharing paused again?
It seems to be. I think you might need to relaunch. Just go ahead and unshare and reshare. Some kind of gremlin.
Right. How's that?
Yeah, that's working. I have your presentation. If this doesn't work, I can share it.
Is that working now?
Try advanced. Yes, it is. It is.
Okay. We have maps and some figures here and a
Yes.
laser pointer.
Yes.
Great. Okay. So third time's the charm, right? So yes, this map on the left shows the states that currently produce geothermal power in the US. And they're ranked by the most producer to the least producer. And really, there's only 7 states that produce geothermal energy here in the US. Down here, we have kind of it's divided up by how much energy, geothermal energy, each state produces. Out of the total geothermal budget, California produces the most at 66%, but that only makes up 5.1% of the total energy that California produces, total electricity. And if we look at Nevada, they make up 26% of our geothermal portfolio, but that only makes up 10% of their total energy budget for the state. So we have a lot of room to grow. Over here on the right, this is another figure from EIA showing just the fuels we use to generate electricity. Natural gas makes up about 43% of our energy portfolio, coal at 16, nuclear at 18, and renewables are up to 21.5% now. And then this figure over here, this part of the figure shows the breakdown of different renewable sources. Wind comes in at about 10%, hydroelectric at 5%, solar, biomass, and geothermals all the way down here at the bottom at less than 0.5% of our total power generation in the US. And I forgot to mention on the previous figure, our installed generating capacity in the US currently, or at least as of 2024, for geothermal energy is 3.9 gigawatts. So we have a lot of room to grow, and I think that's why we're all here today, is to figure out how we can really increase geothermal's footprint over the next couple of years and decades. This is another figure from EIA showing just how our fuel usage has changed through time. We can see this big decline in coal over the past 15 years, and natural gas has stepped up to take that place, especially with our unconventional oil and gas resources. Nuclear has been pretty stable, and then our renewables have been growing slightly over the past 10 or 15 years. Over here, this is a figure from Augustine 2017. This came out of the National Renewable Energy Lab. And it's showing the average installation cost in dollars per kilowatt. Over here on the left, we have our combustion turbines, so our natural gas systems. Those are obviously the cheapest to install now. And since this is from 2017, this might be a little dated now. These numbers might have come down a little bit. And most of our renewables fit here in the middle. And what we're going to be talking about today and throughout this workshop is geothermal and sedimentary basins. And based off this figure, it's showing that the installation cost is very high compared to other energy resources. So we need to work together as the geothermal energy, the oil and gas industry, to really determine how to drive these costs down and make this an efficient energy source for us to develop. Additionally, I like to show kind of the breakdown of global geothermal energy production. This figure is from Think Geoenergy, if you're familiar with that website. And it shows that the US is actually the top producer of geothermal electricity in terms of installed capacity in the world, which is amazing. A lot of people probably think, Iceland is one of the top producers. And they do. They produce 30 or 35% of their total electricity from geothermal energy. But since it's such a small country, they only produce a total of 754 megawatts, where we're producing almost 4 gigawatts here. So a big difference there. So to get started, since I'm the introductory lecture today, I'm going to talk about, what is geothermal and go through some of the key definitions so we're all on the same page for the next 2 days. So geothermal simply is earth heat or heat from the earth. And the figures I'm going to show on the next couple slides come from this GeoVision 2019 report that the Department of Energy put together. It's a really great report. This is how I got started in geothermal energy. I encourage you, if you're interested and you haven't seen it yet, to go find it, download it, and read through it. It's very, very helpful. And a lot of these figures are going to be from this report. So the first thing I'm going to talk about are our hydrothermal systems. And since we're all coming from the oil and gas space, I've kind of divided these up as conventional and unconventional, how we would think about that in the oil and gas world. So our hydrothermal reservoirs, these are our very hot and permeable conventional geothermal resources. And this is probably what you think of when you think about making electricity from geothermal. Hot steam coming out of the ground, and we can use that to directly make electricity. So in this figure here, we have this fracture network. We're producing steam out of the ground, bringing it through one of these flash or binary power plants to make electricity. We also have enhanced geothermal systems, and these are the more unconventional side of geothermal resources, where the subsurface is hot, but maybe not as hot as our conventional hydrothermal, but we have lower permeability and or lower fluid saturation, so we're going to have to stimulate these rocks for efficient production. So think about us targeting hot, dry rock for enhanced geothermal systems. And these are concepts that have been around since the 70s, but they've really gained traction in the past 10 to 15 years. There's another avenue of geothermal called direct use applications, and this is directly using the hot water or steam that's coming out of the ground for its thermal energy. And we can use this to provide heating and cooling in residential, commercial, or industrial applications. We also have blind geothermal systems. These are subsurface geothermal systems with no surface expression. So a lot of these conventional hydrothermal systems have a surface expression associated with them. They have hot springs or fumaroles or geysers or something to show that there's a working system, hydrothermal system below. And blind geothermal systems are geothermal systems that don't have that surface expression. Then we have geothermal heat pumps, and this is on the kind of opposite low temperature end of the spectrum. And this is just storing thermal energy in the ground beneath residential and commercial buildings that can replace your traditional HVAC systems. There's a whole hour-long presentation we could just do on that, and so we're not really going to be covering that today, so we're going to be focused on the power generation side of things. And then there's super hot rock geothermal. You probably hear this term being thrown around as you're coming into the geothermal industry. And this is targeting superheated rocks above 400 degrees C. So very hot, a lot of thermal energy stored in the ground there, but a lot of geologic and engineering challenges associated with getting that energy out of the ground. Typically, we don't see heat that high in these sedimentary basins, so we're not really going to get into super hot rock geothermal today. So we're mainly going to be talking about sedimentary geothermal systems and what we can find for geothermal resources in sedimentary basins. So the first thing I want to talk about, the GeoVision report kind of skips over sedimentary geothermal, but there's been a lot more work done in the past 5 or 6 years to allow us to understand these systems. So sedimentary geothermal is simply just using these geothermal fluids or these deep brines in sedimentary basins for power generation or a direct use application. We also, within this umbrella, we have the hot sedimentary aquifer geothermal. So this is producing hot brine from a porous and permeable reservoir for geothermal energy. We also have the geopressured geothermal systems, and that's targeting hot, overpressured reservoirs for their energy, or pumping water into a tight reservoir to pressurize it that we can extract when electricity prices go up to make geothermal energy. There's also geologic thermal energy storage, or geotests. I think this is going to be an important part of geothermal, especially in sedimentary basins in the next couple of years. And that's where we're just using the Earth's heat to store thermal energy before we use it. And so there's potential here, and there's been a lot of discussion about how can we use or repurpose depleted oil and gas fields for geologic thermal energy storage. Additionally, there's thermal energy networks. This is kind of part of that direct use umbrella I mentioned on the previous slide. And this is a series of interconnected pipes that distribute thermal energy from a heat source or heat sources to multiple buildings or facilities. And again, there's been discussion about repurposing depleted oil and gas fields that produce hot enough water for these situations. And lastly, there's potential to use these enhanced geothermal systems that I mentioned on the last slide in sedimentary basins too. So instead of going after hot, dry, igneous, or metamorphic rocks, maybe we can go after tight, low permeability carbonates or sandstones, things like that. So those are all the definitions that I wanted to go through this morning. So in terms of types of geothermal reservoirs, when I came into geothermal, I didn't realize this, but it's all types of rocks. You know, we can find geothermal resources in pretty much everything. For our conventional hydrothermal, igneous, metamorphic, and sedimentary rocks. For our enhanced geothermal systems, it's been mainly igneous with some metamorphic, going after that hot, dry rock. But now there's potential that we could maybe look in the sedimentary basins for these tight rocks and target those. Sedimentary basin geothermal, looking at carbonates, siliciclastics, and even potentially evaporites. And then regardless of all these reservoirs, fractures are going to be very important for producing water and steam to make electricity. On the right here, this is another GeoVision figure showing this thermometer with different temperatures on it, and our power generation or direct use applications on the left and the right, respectively. Our conventional hydrothermal really fit up here in the really high temperature part of the systems, along with hydrogen production as a direct use option. And your more unconventional power generation sources are EGS and sedimentary basin geothermal. They'll fall in the middle kind of range of this thermometer here. And there's all these direct use applications, which is a whole concept and energy sector in itself that we're not going to be getting into today. But there's potential for an enormous resources just using the thermal energy for heating and cooling options. Okay, so now we're going to talk about each one of these systems in a little bit more detail. For our conventional hydrothermal systems, we'll have a heat source, typically magma in the subsurface. That heat is flowing up through the subsurface into somewhere where we have this fracture network that's filled with water, allowing that water to turn to steam. There's typically a reservoir caprock that keeps that steam underground, and maybe there is a surface expression where we have steam discharge or a fumarole. But what we can do here is drill a well into that fractured steam reservoir, produce steam directly out of the ground, run that in through a power plant to spin a turbine, spin a generator, and make electricity. And then we can re-inject that cooled steam or water back underground to be reheated again. This is an example from Iceland. This is a picture I took when I was there 2 years ago of the Krafla geothermal power plant in Iceland. It's a 60 megawatt power plant that's been producing for almost 30 years now. And when I saw this, it reminded me of a conventional oil and gas field that we're familiar with. We have a series of well pads and production wells around the exterior here. They're feeding steam through a pipeline to the central processing facility. And then that steam goes into this hydrothermal power plant where they use it to make electricity. And then they can re-inject it into a cooler part of the system. And because I'm a big geology nerd, this is me standing under the pipelines way over here. And this is what I did on my birthday 2 years ago. How these power plants work, there's really two designs here for dry steam power plants and flash steam power plants. When you're producing just steam out of the ground, you can use a dry steam power plant, and the steam comes out of the ground, goes into the turbine, spins that, which spins a generator to make electricity, and then you can condense that cooled water or steam and re-inject it back underground. For these flash steam power plants, this is when you're producing two phases out of the ground. So you're producing steam and water, and you can't send that water through your turbine. That'll cause some engineering issues. So you have to strip that water off and remove it from the system. And now people are actually installing a different type of power plant on the water side of these to extract extra energy from this system. So these are the two types of power plants that we typically use in these medium and high temperature systems where we're producing steam out of the ground. But now people are interested in using these binary cycle power plants that we'll talk about in a couple slides in these conventional hydrothermal systems. This is an example of the Geysers hydrothermal power plant in California. It's the largest geothermal power plant in the US and maybe the world. It consists of 13 operating geothermal power plants, which use 319 steam wells to produce steam out of the ground. All this data I just pulled off Calpine's website. They're the operator of this geothermal field, but it produces 630 net megawatts of power, or that's what the power output of these facilities are. And I pulled this figure from their website because when I looked at it, it reminds me of our petroleum system elements. We have our source rock, which is our magma. That's our heat source. We have our permeable reservoir. We have our reservoir caprock, our top and seal. And we can drill wells into this permeable steam reservoir and produce that to make electricity. And, if we're thinking about the petroleum system elements here, our timing and migration would be the thermal conductivity and the heat flow in the subsurface here. So really, a lot of these geothermal systems share similar petroleum system elements. For enhanced geothermal systems, now these are a little bit different. Like I said, they're more on the unconventional side of things. So with this, what we would do is we would drill a series of horizontal, deviated, vertical, or any combination of those type of wells into this hot, dry rock. And then we can hydraulically fracture this hot, dry rock to make an engineered reservoir. Once we have that reservoir in place, we can pump down a fluid, whether it's water or a working fluid, to be heated in the subsurface in this engineered fracture network. And then we can pump it out with this production well and run that through a specialized power plant called a binary cycle power plant to make electricity. There's a really great example of this called the Forge project going on in Utah. If you Google Utah Forge, if you're not familiar with this, you can pull up their website, and they have all the data they've collected over the past couple of years from drilling wells into hot, dry basement rock, and you can go look at it for yourself. But what they've done here, so we're in the Great Basin, we're in Utah, it's an extensional basin, and we'll talk about what those are in a couple slides. But they drilled through the sedimentary basin fill up here, and they drilled into the granitic basement, and they've drilled a series of horizontal wells and built this fracture network where they can inject water, move it through the fracture network to be heated up, and extract it to make energy. And this is a big laboratory for understanding how EGS systems work here in the US, but it's really a phenomenal project for testing out these concepts. And so for these lower temperature systems, or medium to lower temperature, I should say, for EGS and sedimentary basin geothermal, we use what's called a binary cycle power plant. And this is where, we're not producing fully steam out of the ground. We're mainly producing water, maybe a little bit of steam. And so that comes out of the production well, and that goes into a heat exchanger. And that's where we pass the thermal energy from the hot brine that's being produced out of the ground to a working fluid. And these working fluids are low boiling point fluids like butane or ammonia. There's plenty of other ones out there depending on engineering requirements. People even talk about using supercritical CO2 here. And we pass that thermal energy to this working fluid where it expands, it turns to a gas, creating high pressure. And now we can use that high pressure gas to spin a turbine, which spins the generator to make electricity. And then we recondense that working fluid into a liquid and move it back into the heat exchanger to repeat the process. And then the condensed or cooled water can be re-injected underground into the same formation or disposal formation, depending on the type of project, to be reheated again. And a lot of times you'll probably see in the literature the organic Rankine style type power plants, or ORC. Those are commonly used types of power plants these days, and they're a type of binary cycle power plant. Moving into the sedimentary basin geothermal world, here's an example of a hot sedimentary aquifer project going on in Canada. This is a figure from Deep Earth Energy Production Company. It's a Canadian geothermal company. They're operating in southern Saskatchewan, and they're drilling wells into the basal sandstone in the Williston Basin, and they've drilled a series of horizontal wells into the sandstone, and they're producing hot brine from this formation up to one of these binary cycle power plants where they can use it to make electricity. And then they can re-inject the cooled brine back into the same formation through these injection wells to move through the permeability, move through the matrix to be reheated again, and kind of work in this cycle. And so with these resources, we're looking at on the lower end of temperature, 200 to 300 degrees, depending on the application. And we'll be talking about these more throughout the presentation. For well designs and fluid types, to finish up all of our definitions so we can really get into the fun stuff here. Brine, we're probably all familiar with brine coming from the oil and gas side of things. These are hot saline formation waters, produced from an underground reservoir that we can use for power generation or direct use application. The working fluids, like I mentioned, these are low boiling point fluids that we can use in these binary cycle power plants to spin a turbine and make electricity. There's a lot of different types of working fluids. We could probably do a whole hour-long discussion on what working fluids on and their requirements, but we'll leave that for another workshop. In terms of types of wells, there's open loop wells, and these are the ones we're familiar with from the oil and gas world. These are perforated wells that we use to access fluids from underground. So we can either produce fluids from a reservoir using an open loop well, or we can re-inject fluids back into a reservoir using these open loop wells. There's also another side of geothermal called closed loop or advanced geothermal systems. And these are using fully cased wells to circulate a working fluid into the subsurface to extract thermal energy. So the working fluid within the wellbore doesn't interact with the formation at all, and any fluids in the formation don't interact with what's in the wellbore. We're just circulating a working fluid. Two examples of this really quickly. This is from Greenfire Energy. From their website. This is kind of like a hybrid open loop, closed loop design, I would say, where they have this wide diameter wellbore, where they're repurposing existing wellbores. They have hot brine in the bottom that's come out of the reservoir, and they can put down this closed loop advanced geothermal system where they circulate a working fluid down to the reservoir, allow it to heat up, and bring it back to the power plant to make electricity. This is another example from a company called Ever, where they have intersected a horizontal well with a vertical well, creating this U well loop design, and they can just circulate a working fluid through this fully cased well to extract thermal energy from underground. So that's another way we can make energy from these sedimentary basins or hot dry rock too. Okay, so let's move into more about sedimentary basins, since that's what we're all here for today. I like to start with this map. This is temperatures at 6.5 kilometers, or about 21,000 feet, from the SMU Geothermal Laboratory. And again, if you're new to geothermal, I encourage you to go look at all the great work that SMU has done over the past 15 or 20 years, putting up nationwide maps and doing some small case studies too. A lot of great work out there. And I like this map because it shows where places are hot and where places are cooler. Of course, orange and reds are hotter here, and greens or yellows are cooler. And if you think back to that first map I showed where we produce geothermal energy currently in the US, you can see why. The West is very hot for obvious geologic reasons. We have elevated heat flow related to active volcanism, ongoing volcanism. We have elevated heat flow in the basin and the range due to crustal extension, where we're thinning and attenuating the crust out there, and we're allowing for higher heat flow from the mantle. We have the Rio Grande Rift, which is another extensional regime, the Yellowstone hotspot, the Cascades. We just have a lot of hot things going on out to the west. But me being a sedimentologist and a stratigrapher, when I looked at this map first, I was like, well, that's cool. Well, I should say hot. But why is the Williston Basin, the DJ Basin, and the Gulf Coast popping out as so hot, whereas other mid-continent and Rockies basins are not? So that got me thinking about, well, how can we go and look at geothermal in these different sedimentary basins? So switching gears real quickly, we're going to cover sedimentary basins rather quickly, and we're all familiar with these different type of basins, I'm sure. We have our extensional and our rift basins, like we have the Rio Grande Rift or the Basin and Range Extensional Province. We have our passive margins, like the Gulf Coast or the eastern margin of the U.S. We have our intracratonic basins, like the Williston Basin up here in Montana, Wyoming, and southern Canada. And then we have our foreland basins, like I'm at here in the Colorado, Denver area. And so thinking about the morphology and how these basins are created, we can start to think about, well, where do we look for geothermal resources in these different types of basins? So this is an example of an extensional basin from the Great Basin National Park's website. I think it's a really great cartoon to illustrate how these Horst and Grobman features work. And since we're pulling the crust apart here, we separate and have these Horst and Graben features opening up where we have these down drop blocks creating these big valleys. And they get filled with these sedimentary basin fill. And traditionally in oil and gas, we would only be looking really at resources in this sedimentary basin fill. But now think about geothermal. I just showed enhanced geothermal systems. I showed that Utah Forge project where they've drilled into the hot, dry rock that makes up the horst blocks here in the mountain ranges. We could also look for conventional hydrothermal resources where we have convective fluids coming up these fault zones. And we could also look for hot sedimentary rocks in these extensional provinces. Moving on to passive margins, these are very different than our extensional basins. They started off as an extensional basin, and then they transitioned into this passive margin, which is just basically a thick wedge of sediments that's prograding and building out into these basins. And so, where we look for geothermal resources and the size and type of reservoirs is going to be very different than compared to these extensional basins. And this is an example from the Gulf Coast. Looking at our intracratonic basins, again, these are very different than the last two types that we looked at. The Williston Basin here, this is an example from North Dakota State University's website talking about, how the Williston Basin is set up and what it looks like stratigraphically. And this is a large sag basin that's been accumulating sediments since the Cambrian. So where and how we look for geothermal resources is going to be different here. And lastly, looking at foreland basins, these are asymmetric basins that form in compressional tectonic regimes. And again, where and how we look for geothermal resources in these asymmetric foreland basins is going to be very different than how we explore it in extensional and passive margins. So we need to think about that as we're looking for geothermal resources in these different types of basins. Okay, so once we're in these sedimentary basins, there's a couple different projects we can pursue. Over here, these are different types of geothermal systems we could be looking for in these sedimentary basins. We have our hot sedimentary aquifers, our enhanced geothermal systems, hot dry rock, our advanced geothermal systems using those closed loop wells. We have our geopressure geothermal systems. We have our geologic thermal energy storage and thermal energy networks, or direct use. And so kind of the low-hanging fruit people talk about these days is just co-production with oil and gas resources. So say you have an oil and gas field that's producing hot water. We can strip that off at the separator on the production pad and potentially use that to make electricity or for a direct use application. Now, the key advantages here is low cost. We have the existing infrastructure in place. We have the roads, the pipelines, the power lines, everything there, and the temperature's known. The reservoirs have been well characterized for oil and gas production, so we know a lot about it. The key disadvantages here is, these wells were drilled for oil and gas, so they're not necessarily in the right location or the right size or type for geothermal energy production. Additionally, if your oil and gas field has kind of reached the end of its life and the water cuts have gone up really high and maybe it's watered out, we can repurpose these fields or wells for geothermal energy. Again, similar advantages and disadvantages here is that, these wells were drilled for oil and gas. They might not be perfect for geothermal, but there could be options to convert your depleted oil and gas field into a geothermal resource, whether it's a hot sedimentary aquifer, or we can use it for geologic thermal energy storage, or maybe a thermal energy network. Lastly, of course, we can explore for new geothermal fields in these sedimentary basins. Key advantages here, the well location. We can pick exactly where these geothermal resources are and go after them. We can go after the exact formation we want to target and produce water from or extract thermal energy from. And we can control the size and type of well bores. We can drill wide diameter vertical wells. We can drill long horizontal wells, whatever you want. What do you think's best for extracting that thermal energy out of the ground? Of course, the main disadvantages with exploration, as we all know, is that it's the most expensive and risky option. So what are we exploring for, particularly with hot sedimentary aquifers? And, that can go into geologic thermal energy storage and a couple other of those geothermal systems. This is a cross plot from NREL again, the National Renewable Energy Lab, from a 2017 publication. And I like this because I think it does a good approximation of suggesting what we need to make electricity from hot sedimentary aquifers and geothermal resources in sedimentary basins. On the x-axis here, we have temperature in Fahrenheit or Celsius, whatever you prefer. And then on the y-axis, we have flow rate in barrels per day or liters per second, whatever you prefer there. Since I'm a ex-oil and gas guy, my brain just works in Fahrenheit and barrels per day better, but whatever works for you. And so the curves we have on here in blue, red, and green respectively are 1, 2, and 4 megawatts of electricity. So the example I have here is if we have 300-degree Fahrenheit brine, and we want to make 4 megawatts of electricity, we need about 65,000 barrels per day of fluid. So that's a lot of fluid, right? And if we just have or reduce the temperature by 50 degrees to 250 degrees Fahrenheit, we need over twice as much fluid to make the same amount of electricity. So you can really see that this is showing that temperature is really driving efficiency in these systems. And, this isn't, 100% correct, I would say, but I think this is, puts us in the ballpark of thinking what we need geologically and engineering wise to make electricity from hot water stored underground. And so in order to achieve this, well, what do we need? Of course, reservoir temperature is important. 250 to 300 degrees, depending on who you talk to and the type of reservoir and power plant design and depths and things like that. It's kind of the minimum temperature required for commercial scale power generation. There are all, of course, some caveats to that, depending on who you talk to. And of course, to get that, we also need reservoir deliverability and storage capacity. So we need tens of % of porosity and thick reservoirs, most likely. hundreds of millidarcies of permeability, and of course, fracture permeability, whether it's natural or engineered, is definitely going to help here. Reservoir pressure is a double-edged sword. High pressure is good for lifting brines from these deep reservoirs. So in order to get to these temperatures in these sedimentary basins, typically we have to drill pretty deep. But then if we're going to re-inject that hot brine into a high pressure reservoir, we're going to use a lot of electricity, have a lot of parasitic loss with these power plants and these well designs to re-inject to those deep reservoirs. Low pressure is good for re-injection capabilities, but again, we're going to have to use electricity to pump water from these deep reservoirs, creating that parasitic load again. So this is kind of a general idea of what we're looking for in these sedimentary basins, particularly for hot sedimentary aquifer geothermal. And so since we're all pretty familiar with porosity, permeability, maybe hydraulic fracturing and pressure, I'm going to focus on reservoir temperature for the rest of the presentation, just because that's something I've been really working with my dissertation, and I've run into a lot of different issues in sedimentary basins trying to unravel reservoir temperature. So this is a map from another SMU publication talking about or showing the location of bottom hole temperature measurements and their depths as of 2004. So this is a little dated, but it does a good job of showing where we get bottom hole temperature data from. And bottom hole temperature data is the dominant temperature data set that we have in these sedimentary basins. And we'll talk about why on the next slide. And so on this map here, they have the well locations colored and shaped based off their depths. So the red squares and the brown circles are the deeper bottom hole temperature measurements in these different basins. And so you can see that the Gulf Coast, the Permian Basin, Anadarko Basin, and these Rockies and Mid-Continent basins really have the deepest deepest data set of bottom hole temperature measurements. And we're going to use bottom hole temperature, of course, for isotherm mapping. So looking at how temperature and depth is related. In oil and gas world, we use for maturity mapping and basin modeling, and we'll be using basin modeling here in the geothermal world to calculate geothermal gradients and understand how the geothermal gradients change in these different basins. Play fairway analysis, of course, understanding engineering requirements for power plants, surface facilities, and subsurface drilling hazards, and then, of course, for our geothermal resource assessment. So this bottom hole temperature data is very important for exploring for geothermal resources in sedimentary basins, and particularly sedimentary basins that lack that elevated heat flow from ongoing volcanism or like active crustal extension. Okay, so what are bottom hole temperature measurements? Well, bottom hole temperature measurements, BHTs, are temperature measurements recorded on our electric logging tools when we drill and log a well. And these temperatures are stored on the log header for each one of these logging runs. These can be done, there can be one or multiple temperature measurements depending on how many logging runs were done. And there's an important factor here, which we'll be discussing over the next couple slides, and that's the time since circulation. So the time since we stopped drilling, stopped circulating drilling mud to the bottom of the hole, and then subsequently removed the drill bit and the drill pipe from the hole and got the logging tools to the bottom of the hole. And that's called the time since circulation, or TSC. And it's important to note that these bottom hole temperatures are not the true formation temperature. They are measuring the temperature of the drilling mud at the bottom of the hole or where the measurement was taken. So typically these don't represent the true formation temperature, whereas it's just the temperature of the mud at the bottom of the hole. This is a little schematic showing just how this works. We have a logging truck over here, and we're lowering these tools down the hole, getting a bottom hole temperature measurement here. And these are just two examples of some tools, some logging tools I pulled from just Google search. And I wanted to show this because these tools can be very long. This is what's called a triple combo log. I'm not going to discuss all the different tools that are on it, but we do have the temperature measurement or the thermometer down here at the bottom of the tool. You know, this is 34 meters tall, so we're talking almost 100 feet tall for these logging tools that we're lowering down the hole. This is Schlumberger's Platform Express. You know, again, it's 40 feet tall. So this is a long series of tools that we're lowering down the hole to get these different electric measurements and temperature measurements. So some of the controls on subsurface temperature while drilling and logging, I think this is very important to understand. And I think if you're going to be using bottom hole temperature measurements for temperature mapping and geothermal exploration, you need to be familiar with well site operations, both from the drilling and logging side, so you can look for potential issues with the data. So when we're drilling, we're all probably familiar with this, but I'll just recap. We are pumping drilling mud down the inner annulus of the drill pipe down to the drill bit where it comes out the bottom of the hole. And it does that. We do that for a couple of reasons. One, we want to lubricate the bit. Two, we want to keep things cool at the bottom of the hole. Three, we want to remove all the cuttings from while we're drilling. And four, we're using it to control any formation pressure. So we want to hold back any oil and gas or water that's wanting to come into the wellbore and to keep the hole stable. But this mud sits in earthen pits or in metal tanks on the well pad, and so it's exposed to the ambient surface temperature while we are drilling. So it's typically cooler than the subsurface. Once we get down, 1 or 2,000 feet, where typically the mud is going to be cooler than the surrounding formations. So as we're pumping and circulating mud while we're drilling, we're actually extracting thermal energy from the rocks surrounding the wellbore. So we create this zone of cooling around the area we're drilling. Now, in order to log these wells, of course, we have to take the drill pipe and the drill bit out of the hole, so we can't circulate mud anymore. So the mud is just sitting there stagnant in the hole, but it is slowly being warmed up by the thermal energy coming back out of the formations into the wellbore. And so we get the logging tools to the bottom of the wellbore, and then we can take our temperature measurement. But there's still other controls and bottom hole temperature measurements while we're logging. There's that time-sent circulation factor I talked about. The mud type and its properties, whether it's water-based or oil-based, is going to control how fast that wellbore heats up again. Thermal conductivity of the formations, the formation temperature, the reservoir fluids, the vintage, and the type of logging tools. For the data set I'm working in my dissertation, there's wells that range or temperature measurements that range from early 50s all the way to present day. So that's going to affect your accuracy of your temperature measurements. And then the number and speed of logging runs, and also human error is a big part of it. It's easy to write down the wrong numbers here, and so that's a part of the that we need to consider. Where is BHT information stored? Well, it's simply just stored on our well header information. We're not going to discuss a lot about well headers because I'm sure everyone here has looked at those before. Of course, we have our location, elevation information up here at the top, and all of our logging data is going to be stored down here. Our logging runs are stored at the top here, 1, 2, 3, 4, 5, 6, and 7. I particularly pulled this well header because it's a very interesting well. It has 7 logging runs taken over the course of 11 months. So it's very interesting from a geothermal standpoint. The bottom of our logged interval is here. That's important for geothermal exploration. Here's our mud property information. We're not going to discuss that today, but our time-sent circulation information comes from down here. This is where it shows that our circulation was stopped at 12:30 on February 10th of 1983. And then the logger got the tools to the bottom 5 hours later. So that's our time-sent circulation. And you can see how that would change with the different logging runs. And our maximum recorded temperature for the different logging runs is down here just below that at 6,500 feet where this first logging run was done. It's 140 degrees Fahrenheit. And where the 7th logging run was done at 24,000 feet, it's 435 degrees Fahrenheit. So this is where all of the data that we're going to be using to understand temperature in the subsurface typically comes from in these sedimentary basins. You can also get equilibrium temperature data in terms of cement bond logs, and we call them equilibrium temperature data because these are temperature measurements on different tools that are taken well after we stop circulating. So we're hoping that the mud at the bottom of the hole is back to its true formation temperature. So we can get that data on cement bond logs. We can also get that data from cased hole temperature logs, which are just a temperature logging run we do once we fully case the well. And we can also get that temperature data from drill stem tests. And I'm not going to go through what drill stem tests and how they work are, but it's an important place to find additional temperature data that we consider closer to equilibrium or true formation temperature. And what's good about drill stem tests is typically they record a time and multiple temperatures, so you can see how the wellbore is heating up through time as the tools sit in the bottom of the hole. Okay, So because there's so many variables that go into or that affect these temperature measurements, we have to do a correction to try to get back to that true formation temperature, since typically these temperature measurements are cooler than they should be. And so there's two important things here. One thing to consider is that temperature correction can vary by basin, both geographically and the type of basin. And temperature correction can be variable based on the type of data available. So if we don't have that time set circulation data, you can't do some of the correction methods that require it. And then I've summarized some of the more common sedimentary basin bottom hole temperature correction methods in this table. I've divided them into a variable-based and a depth-based correction methods. There's this Waples equation that uses time sent circulation, depth, and surface temperature to correct for those factors. That was developed in the Gulf of Mexico. There's a Horner correction, which uses 3 or more temperature measurements at the same depth, which is probably one of the more accurate ways to correct. But with these bottom hole temperature data sets, we don't typically have 3 measurements at the same depth. There's a Brennan method, which takes temperature measurements while drilling. That's more common in the geothermal world, and we just lack that data set typically in the oil and gas world. As far as depth-based methods go, we have the Keel, Forrester, SMU Harrison, and Crowell. These were all developed using that equilibrium temperature data, drill stem tests, case level temperature logs, et cetera, to develop an equation in these different basins across the US. So it's important to choose the right method based on the basin and the type of data available. So with that, we'll switch to a case study I'm working on for my dissertation on the Gulf Coast to give you an example of some of these bottom hole temperature measurements and challenges to correction. On the right here, I have what I'm calling my geothermal elements of the Texas Gulf Coast. And this is all work done by previous researchers. I want to acknowledge that. There's been a lot of great work done on the Gulf Coast looking at the geothermal potential there. The depth to 250 degrees Fahrenheit is important across the Texas Gulf Coast because, like I said, that's approximately the minimum temperature for electrical power generation, depending on a couple different variables. And what this map is showing, and these are contours from, again, from SMU's Geothermal Laboratory, some work they've done. But in these peach colors, that's where 250 degrees occurs about 9,000 feet in South Texas and East Texas, and at 10,000 feet across the greater Gulf Coast trend. The location of geopressured zones is important. These are these blue and purple striped polygons, and these are highly overpressured sandstones in the Paleogene, Wilcox, and Frio formations. And these were identified by the Bureau of Economic Geology of Texas and the Department of Energy back in the 1970s as potential geothermal resources out here. And they were particularly looking at these highly overpressured zones because that was the only way to achieve the high flow rates required to make electricity from hot water. But now with horizontal drilling and hydraulic fracturing, maybe we don't have to go after these highly overpressured zones anymore. We can go after kind of normally or slightly overpressured zones. And that project, the Department of Energy and BEG project, they actually drilled a vertical well just south of Houston in 1979, and they produced enough hot water to make 1 megawatt of electricity using one of these binary cycle power plants. And it was a great proof of concept for Gulf Coast geothermal. The blue and green lines on here are Cretaceous shelf margins, and these are important because our porous and permeable reservoir is going to be north of those shelf margins. There's over 80 salt diapirs on the Gulf Coast, and I think these are important because they're dominantly made of halite, and halite has a much higher thermal conductivity compared to the surrounding siliciclastic and carbonate rocks, so they could be a potential geothermal resource. And then lastly, the underlying crustal types. Most of Texas is underlain by this Proterozoic craton, but we do see that when we get into the upper part of the Gulf Coast, it's underlain by thick transitional crust, and then the lower part of the Gulf Coast and the shelf is underlain by thin transitional crust. And again, if we kept going out into the Gulf of Mexico, we would find oceanic crust. But a lot of the heat here is being derived from radiogenic decay in these distant crustal types, so that's going to have an effect on the ultimate heat flow that's coming up from the crust into the sedimentary section. And so because of this, I identified 4 interesting areas with these different geothermal elements, and I picked South Texas to work because it has all 5 of these overlapping geothermal elements. Zooming into South Texas, these are the same geothermal elements, but I'm showing the well data that I'm using for this geothermal project. This is a well log based project. TGS, I have to give a shout out to them. They're one of our sponsors of our research group at Colorado School of Mines. And they let me root around in their database And I put together a data set of 3,407 vertical wells with digital log data deeper than 7,000 feet to make some of these interpretations. And this is well count versus depth in this area of South Texas to show that we really drop off pretty quickly, but we do have a couple wells that get down to that greater than 20,000 foot depth mark, which is really helpful for understanding heat flow in the deep parts of the basin. For temperature data, I have a slightly overlapping data set of 1,862 wells that I was able to put together with one or multiple of these bottom hole temperature measurements. And then I wanted to really think about this geologically. So I divided it into two data sets, a Cretaceous data set shown in green, made of 826 wells with bottom hole temperature measurements in the Cretaceous formations, and another 1,036 wells with bottom hole temperature measurements in the Paleogene formations. And as a caveat to that, these aren't all the bottom hole temperature measurements in the area. This is just what I was able to scrape together for this project. And we're looking at the uncorrected temperature versus depth here. Okay, so I really wanted to think about temperature geologically out here. So since I divided into that kind of binary Cretaceous and Paleogene systems, and I had over 3,000 vertical wells with well logs out here, I was able to build a really nice stratigraphic framework across the area, and I was able to place where each one of these bottom hole temperature measurements are. So over here on the left, this is the map showing the bottom hole temperature data. The green circles are my Cretaceous bottom hole temperature measurements. There were 826 of them. And then 272 of those had both time-sent circulation data from well log headers and digital logs. So I started with that data set because I thought that was going to be the best data set to use. And that data is plotted up on a temperature depth plot here. And I've colored this by the different Cretaceous and Jurassic formations. So the dark blue is showing the Smackover. The light blue, the Sligo formation, so on and so forth. This is my Mesozoic type log showing gamma ray on the left here from 0 to 150. And the greens and blues are lower gamma ray, and the yellow and grays are higher gamma ray. Depth is in feet here. The Cretaceous section is over 10,000 feet thick, and the Jurassic section below that is a couple thousand feet thick too. Deep resistivity and then bulk density. And I've shaded bulk density pink and purple where we have higher density rock, and then yellow and green where we have lower density rock. And these are the different formations that I've been looking at for their geothermal potential in the Jurassic and the Cretaceous section. So I ended up using that Waples correction method to try to correct these bottom hole temperatures. That equation is shown here, and that incorporates the surface temperature. So that's the average monthly temperature for the county and year that the well was logged, which is not a number that's stored on your well log header. So I had to go dig this out of a NOAA database because that's ultimately going to affect your mud temperature when you're logging the well. The formation factor F is based on that time-sent circulation data. And then the uncorrected bottom hole temperature measurement and depth comes from your well log header. So you put that all into the Waples equation. And for this data set of the Cretaceous and Jurassic wells in South Texas, I saw on average a 20% increase in temperature from uncorrected to corrected bottom hole temperature. And that's uncorrected is in black, and corrected bottom hole temperatures are shown here in green. And so I pulled in some of that equilibrium temperature data, the drill stem test, and the cement bond logs here to really try to make sure these calculations were correct. And in general, they seem to fit with that cloud pretty well. But once we got below 15 or 16,000 feet, they seem to deviate from these red and yellow equilibrium temperature logs to the corrected bottom hole temperature data. So I went ahead and ran the depth-based equations too. Even though they weren't quite developed for this basin, I wanted to see what it looked like, and I got some interesting results here. We're seeing anywhere between a 12.5% and 20.5% increase in temperature with each one of these correction methods, which is a pretty big difference. And that's a little concerning for me for the geothermal exploration world because we need to be so precise because the margins in geothermal are pretty thin, and having this widespread in temperature correction is a little concerning. And so, maybe the Waples and this forestry equation might be overestimating temperature at depth, whereas the SMU and Kiel might be underestimating. And so you can think about this data and these correction methods a couple different ways. You could kind of use this as a P10, P90 way to find your end members of temperature and risk that geologically. You could try to use, one method in the shallower subsurface, and then another method in the deeper section. And kind of what it's telling me is that maybe we need to develop new bottom hole temperature correction methods for these deeper geothermal resources and in specific sedimentary basins and maybe even specific formations. So I took that data set and I just calculated geothermal gradient for this area of South Texas, and I plotted that up here on this map, this contour map. The average geothermal gradient was 2.66 based off that data set. That's shown in white. And then higher geothermal gradients are in red, where you'd see a hotter potential area, and lower geothermal gradients are in blue. And really, when I put this map together, it's just a computer gridded map, and I wanted to use this to identify potential erroneous data. And, it's not a great map. There's a lot of bullseyes. It doesn't make sense geologically. But what it does help do is identify some of these potential issues with some of the data. And so on this cross plot, we have geothermal gradients that I've calculated up here in degrees Fahrenheit per 100 feet, and then depth of the temperature measurement that went into the geothermal gradient here on the y-axis. And of course, I've colored it by the different Cretaceous and Jurassic formations. And when I started looking at this, there was pretty a large spread of data. And so I went back to the mud logs and the well log headers to try to figure out why we have such a wide spread in this data. And you end up seeing a lot of interesting things here. On the lower end of these geothermal gradients, I can explain a lot of these low geothermal gradients and abnormally low temperatures with drilling and logging issues. These wells in the deep Jurassic were drilled very, very slow for the last couple thousand feet. They were deep exploration wells, which were the first of their kind in the 1960s and 70s. And so I think they just overly cooled the formation while drilling here, and then threw the logs down there, got the temperature measurements, got their logs, and then pulled them up the hole. There's also different density muds that were pumped. There's an abnormally high time circulation, which is always alarming in my head. On the header remarks for this well, it said the thermometer was broken. So, there's your issue. This well was taking losses while they were logging. So that's going to create problems as that cooler mud is falling down the hole towards the logging tools. So a lot of the lower temperature measurements that seem abnormally low, I could explain with drilling or logging issues. So you need to watch out for those with these data sets. Whereas the higher temperatures, they have more of a geologic explanation. I have adjacent to uplift here. These are wells over here in Dimmitt County that are on the Laramide Chittim anticline. So it's an area where we've uplifted and brought those hotter temperatures closer to the surface. These two wells are on the flanks of those diapirs. So we're seeing those elevated geothermal gradients because of that high thermal conductivity of those salt diapirs. And so I'm showing this to say, I try to put together a very clean data set of temperature data, and I'm still finding issues here. So just be very cautious when you're going through and using these bottom hole temperature measurements. Be sure to understand how these wells were drilled and logged. And so to finish up here, because we are out of time, talking about temperature data, temperature mapping is complicated. Don't be cavalier about it and be a detective. There's a lot of variables that affect the quality of bottom hole temperature measurements. And so we maybe even need to consider new intrabasinal correction methods. And we need to consider all the geologic variables that affect the subsurface temperature here. And we also need to approach temperature mapping like petrophysical mapping. We need to QC the data. That's going to be most important. You're not going to map porosity with bad bulk density logs, right? Hand contouring maps to reflect stratigraphic, structural, and tectonic elements, I think, is going to be very important for these kind of prospect level temperature maps. And ultimately, trying to tie that temperature data to reservoir properties is going to be very important. And as far as sedimentary basins goes, there's just abundant opportunities for geothermal exploration. All types of geothermal systems exist in these sedimentary basins. We also need to take a geologic approach to identifying and characterizing these geothermal resources, just like we would do in oil and gas exploration. And lastly, temperature drives efficiency here. And so really understanding accurate subsurface temperature is pivotal here. And this is just a schematic block diagram I put together for my South Texas area. We're not going to talk about the different plate types that are out there, but there's just a ton of uses for geothermal energy in these sedimentary basins. Everything from repurposing and heavy oil extraction for these old conventional oil and gas fields, power and thermal energy for direct air capture CO2 units. The low-hanging fruit is utility scale power generation, green hydrogen production storage, electrical power for data centers, is something that's up and coming, and then direct use for refining or industrial or commercial and residential heating and cooling. And so I have a bunch of references here that I'm not going to go through, but since we're getting started in geothermal, there's just a ton of great references that I want to make everyone familiar with going forward. And with that, we'll call it a day because I am 2 minutes over. So thanks for listening. And if you have any questions, feel free to email me or ask them here. Thank you.